All right. Hello, everybody. Welcome to our first talk of the fall semesters of our point distribution webinar. Just before we get started, little change that we're doing from the summer session is that basically after each talk, after we have questions and everything, we're actually going to be setting time aside so that if anybody wants to stay on and just socialize as one might normally have done for an in-person seminar or conference, we'll be doing that. So, if questions end at about 10, we'll probably do about 10 to 10:30 and see how that goes. So yeah, if you want to stay on after the talk to just socialize, hang out, please feel free to do so. All right, and so without further ado, today as our first speaker for this season, we have my advisor, Dmitriy Bilyk from the University of Minnesota, talking about Stolarski principle, generalizations, extensions, and applications.
Okay, so thank you very much. Thanks a lot for the invitation. It's funny to be the first non-young speaker at this young people's seminar. So that makes me feel a little bit younger. So thanks a lot. So today I'll talk about the Stolarski principle, and it's a pretty intriguing identity that connects to important useful quantities related to point distributions on the sphere and not only on the sphere. So these two quantities are discrepancy and discrete energy. And we'll talk about the original identity that was proved by Stolarski, and then there are countless different extensions, generalizations, or applications to various problems in approximation theory and discrepancy in discrete geometry, and we'll talk about some of those. This talk is meant as a survey, so I want to give you a large sampler of different versions of the Stolarski principle, which essentially means that I will not go into any of the topics too deeply. Okay, so and at least I intended to make this talk very understandable and not too technical. Okay, so let's jump right into it. So let's define the discrepancy, the spherical cap discrepancy on the sphere. So we start with a point configuration Z. So we have n points on the sphere. Okay. By the way, here D will always denote the dimension of the sphere. When I talk about spheres, it's not the ambient dimension, it's the dimension of the sphere. Okay. All right, so we want to measure how well distributed this point configuration is. Okay, and one way to do it is to look at the discrepancy, and the most natural discrepancy on the sphere is the spherical cap discrepancy. So you consider a family of geometric shapes, which are these spherical caps. So they're characterized by the center X and by the height T. Okay, so basically imagine that you're just slicing a sphere by a plane and whatever is above level T, so a plane is at level T, that's a spherical cap. Okay. All right, so then what you do is you look at each spherical cap, and you look at the proportion of your points from Z that fall into that spherical cap. That's this first term here, and you compare it to the surface measure of the spherical cap. Okay, so sigma here will always stand for the normalized surface measure. Okay, so the measure of the whole sphere is 1. So this is a probability measure. Okay. All right, so and the spherical cap discrepancy, the standard supremum discrepancies, you just take the supremum of all spherical caps. So you find the worst possible error, the worst possible discrepancy between this empirical measure and the actual surface measure. And that tests how good your set is. So what are the optimal, or at least almost optimal bounds for this quantity? Well, this was proved by Beck in '84, that you have this lower bound. So this was proved basically by Fourier methods. And you have this upper bound. So there exist sets which satisfy this upper bound, which is almost up to logarithms, almost sharp. Okay. And the upper bound is the only way to prove it with this exact power of log, the only way that I know at least, is using jittered sampling. So you divide the sphere into, so to say, almost equal parts and choose random points in each part independently. Okay. All right. So so here we took the supremum, but of course you can take this quantity in here, and you can take other norms of this quantity. And sometimes it's easier to work with other norms. So for example, you can take L2 norm. Again, that's known as the L2 spherical cap discrepancy. So you're just integrating, averaging over all the caps, over all possible centers and all possible heights of caps. So all possible caps. So instead of taking the supremum, you take the L2 average. So there are a couple advantages to taking L2 averages. First is, well, usually opens the door to Fourier methods, to a variety of Fourier or spectral methods. But sometimes you have an even simpler advantage. Sometimes when you deal with the L2 norm, you can just square things out, compute, and see what happens. And that's what we will do in just a couple slides, actually. So for the L2 spherical cap discrepancy, almost the same bounds hold. So the lower bound here is, as I mentioned on the previous slide, for the L infinity, for the supremum discrepancy, that was done using Fourier analysis. So it was actually done for the L2 discrepancy, for the L2 norm. L2 norm bounds the L infinity norm from below. And there is a variety of ways to show that the upper bound holds. You can construct, in particular, jittered sampling would work also. Okay. All right, so this was also done by Beck. Okay, so for the spherical cap L2 discrepancy, sharp bounds are known in terms of n. Okay. All right. Now I'll jump right to the main subject of the talk. So in 1973, put the year somewhere here, Stolarski proved this remarkable identity, which tells you the following. If you take the spherical L2 discrepancy squared up to some constant, dependent just on the dimension, and you take the average Euclidean distance between your points, so the normalized sum of distances, those two quantities together add up to a constant. Okay, so this is why this is actually called an invariance principle. Okay, so those two things together are invariant, they're constant. Okay, so it's actually very remarkable. It's not just some asymptotic relation. It's not an inequality. It's actually an identity which tells you that minimizing the spherical cap discrepancy is exactly the same as maximizing the pairwise sum of distances. Okay. And you could write this identity in a somewhat different form, okay, which is more common, okay, and you put discrepancy on one side, and then the right-hand side is the difference between the discrete sum of distances here and the continuous distance integral. Okay. All right, so there are several proofs of this principle now. So, as I mentioned, the original proof was by Stolarski in '73. Then there was a much simpler proof by Brauchart and Dick a few years ago. And then a couple of years ago, in a paper with Ryan and Feng Zhai, we gave an even simpler proof. We actually even thought about writing a paper. So Brauchart and Dick's paper is called a Simple Proof of Stolarski Principle. We wanted to write a paper called an even simpler proof of Stolarski Principle, but then just got incorporated into a bigger paper. Okay, so what are some easy consequences of this identity? So immediately you can see some applications. Well, first of all, you can, so first of all, let me mention that the constant that's present in this identity, it's completely explicit. You can compute it, you can find the asymptotics. So that's very simple, and we'll see how the constant arises. There are some applications of this identity that come to mind immediately. Well, first of all, you immediately see that the sum of distances, this discrete energy, must be smaller than the energy integral, right? Because the left-hand side is a positive quantity. Right? So this is probably the most elementary proof of this fact. So this does not use, as we shall see, Stolarski principle itself is more or less an elementary fact. So we do not need to use any orthogonal functions, Gegenbauer polynomials, spherical harmonics. So this is a completely elementary proof of this. Other couple applications that you could do immediately, you could compute the expected value of the spherical cap discrepancy for random points or for jittered sampling. And you could do it very explicitly, even with specific constants. It's not hard to do it even directly, but here you would, if you do it through this identity, because everything splits into pairs so nicely, it's extremely easy to compute. And as I said, you can even get precise constants. Okay. So you actually can get in this case, for example, you can get an identity rather than just a bound. Okay. Okay, so these are some immediate consequences. But right now, let's briefly go over the proof. I will not give you the whole proof of this relation, but I want to show how these interactions appear. So you have this discrete energy, so you can view this as interactions between pairs of points. So let's see how they appear from the definition. So if you write the L2 discrepancy in this way, it's written in the first line here. So I noticed I slightly rewrote the counting part of the discrepancy. I just wrote the sum of the characteristic functions. Also notice one thing, I can easily switch x and zi here because the definition of the spherical cap is symmetric. It's x times zi is greater than or equal to t. Okay, so if I fix t for a moment, then once I square this expression, okay, I would have products of pairs of these terms. Okay, so we'll have expressions of this type. Okay, and if I integrate, I would just get the surface measure of the intersection. Okay, well, this is, if you look at two spherical caps, it's not very easy, at least it's not very nice to write down what the surface measure of the intersection is. But this is where averaging over all heights, averaging over all t comes to help. So now if you average over all t, okay, let's compute this integral. We interchange the order of integration. Okay. And now we see t has to be less than zi dot x and less than zj dot x. Okay, so that's why you're integrating from -1 to this minimum. It has to be less than the minimum. Okay, so you get this expression now. Okay, and now you just write the minimum as 1/2 zi dot x plus zj dot x minus zi minus zj dot x. Sorry. Okay. Notice now when I integrate with respect to sigma, this will disappear after the integration. This will disappear because these are symmetric functions. They integrate to 0. So you will just end up with this expression. And I claim that this only depends on the distance. This integral here only depends on the distance between zi and zj, because I can pull out distance between zi and zj, and then I'm left with this integral where this here is some point on the surface of the sphere. Okay, and by rotational invariance, it doesn't matter which point that is. So here, all dependence on the zi and zj is gone, because I could really put any point here. Okay. Right. So I get 1 minus the constant, and that's precisely the constant I described before, times the distance between zi and zj. Okay. So every talk should have a computation in it. I've done mine. I won't compute things from now on, more or less. Okay. All right. So basically, this explains how these distances arise, and the rest is just a technicality. You can finish the proof. So this is sort of the most important part of the proof. Okay. So you can see that it's completely elementary. You can actually give it to a good calculus student. All right. So let's now talk about generalizations, and well, before we talk about generalizations, let's talk about the energy in a little bit more detail. So we'll define the discrete energy of a point set on the sphere in this way. I normalize the energy. Notice that I will mostly deal with functions that are continuous, so I will not deal with Riese energies in particular. So that's why I do not exclude the diagonal terms here. Also, since I'm on the sphere, I mostly assume that the kernels of the energy are rotationally invariant, and that's why you can write them as functions of the inner product between points. Okay. But in general, of course, you should just put a comma here, and it's just a function of 2 points on the sphere or on the manifold that you consider. So in our example that we saw just now, so the function that you come up with is essentially minus the distance. So if you want to minimize the energy, so you come up with sum of distances. That's the famous problem of Weierstrass, to find in minimizers of the sum of distances on the sphere, of Euclidean distances. And it's not an easy problem, as most of you know. It's on S2, for example, only a handful of optimal configurations are known. Okay, but more generally, when you consider discrete energy, the natural questions to ask are: what are the minimizing configurations? If you cannot find minimizing configurations, what are configurations that almost minimize it? At least give you an almost optimal order of magnitude, maybe. And if you can prove some lower bounds. Okay, so the next slide will actually explain why I'm taking this normalization here. Okay. So I also want to consider energy integrals in the same way, but now instead of sets of points, we consider Borel probability measures, and we take, again, if the function f is non-singular, there is no issue here. If it's, say, a continuous function, or at least or measurable bounded function. So you can define the energy integral this way. So this would be an energy of the measure mu with the interaction given by the function f. And the reason that I wanted to keep the normalization in the discrete energy is because then the discrete energy precisely coincides with the energy integral for this measure here. Okay. All right, and again, a natural question for the energy integrals is: what are the minimizers? When you're on the sphere, there is a natural candidate for minimizer. You can ask if sigma is the uniform surface measure, is that a minimizer? And you can ask whether it's unique. And also, it's natural to look at the differences between the discrete energies and the energy integrals, for example, with sigma. Okay, so basically that would somehow tell you how well Z approximates the uniform measure sigma. So hopefully, at least philosophically, that may lead to some sort of uniform distribution. Okay. By the way, feel free to stop me if there are any questions. Okay, so we will talk about various generalizations of the Stolarsky principle, and generalizations usually will be of the kinds that I wrote down here. So notice that this first pseudo identity that I wrote is essentially repeats the Stolarsky original Stolarsky identity, right? So, but we may be looking at different notions of discrepancy, different notions of distance. You also do not necessarily need to start with distances. You can consider discrete energies for various kernels, and you can I notice I wrote it in a different order here, because when we talk about energy, normally we try to minimize energy, so you usually don't maximize it, although in specific cases, of course, you want to do, but in general, we say we would try to minimize energy. So you want to write it if you're minimizing discrepancy and you're minimizing discrete energy. And usually, if you have some sort of a Stolarsky identity for discrete energy, you can also replace that discrete energy, the discrete measure in the discrete energy, you can just replace it with arbitrary measure. And you can also prove identities of this type. Okay. So why would we be interested in something like this? Well, first of all, you can just get very interesting, remarkable identities. Second, well, as we saw before, if really you have an L2 discrepancy on the left-hand side, it's a positive quantity, then you would get a bounds for sums of distances or for discrete energies. So you would know that the difference on the right-hand side has to be non-negative. Okay. And maybe even if you didn't know which energy integral here you took a priori, maybe if it just works out to be something, you could find what the optimal energy for a certain kernel is. Sometimes, in some specific situations, you would be able to find optimal configurations for the discrete energy if you find the proper notion of L2 discrepancy, which tells you what the minimizers are. And we'll see some examples like this. Okay. So there are, besides just being an interesting curiosity, there are potential nice applications to the Stolarsky principle, and we will see some of them. All right. Okay, so now let's start talking about some generalizations. I told you it's a survey, so I talk about a sampler of different versions. So already in the original paper by Stolarsky in 1973, he actually proved a slightly more general principle than what I stated on the first slide. Okay, so he considered on this sphere, he considered distances which could be represented in this form. Okay, so G is some weight function, and assume you can write the distance this way. Okay, it looks a little weird, but we'll have a couple examples in the next slide. So then Stolarsky principle holds for the discrepancy which is defined with this weight with respect to t, so weighted discrepancy. Okay. Notice that if the function g is equal to 1, you just get the standard spherical cap discrepancy. Okay, but what happens to this distance? Well, you can easily see that when g is identically 1, that then the distance rho is a multiple of the Euclidean distance. Okay. It's essentially the same computation that we've done a few slides ago. Okay. All right. Also, there is another metric that comes up pretty often in geometry. So here, let's write it here. So here in this particular example, d is the geodesic distance from the sphere. Okay. And this distance can also be written as in the form from this previous slide, in this form here. Okay, if you take g to be 1 minus t to 1 minus t squared to the power negative 1/2, you get this distance, and this distance comes very often, and it's also natural for the Stolarsky principle. Actually, there is I probably will not get to it. It's on my last slides, but there is a recent series of papers by Alexander Bargin and Maxim Skriganov about the discrepancy about the Stolarsky principle on finite metric spaces and on the Hamming cube. So in particular, a metric like this comes up there, and it's very natural to consider these a metric like this. So hopefully I can get to that slide, but I'm not sure. All right. And so here we see at least one more application of a distance for which the Stolarsky type identity holds. Okay, well, this approach was generalized by Johann Brauchart to sort of I would say, multilinear case when the function g now depends on more variables. Okay, so you can still write a Stolarsky principle, but you now have a somewhat different quantity here. So this quantity is Well, you take the discrepancy with respect to spherical caps of height t and then height t prime. So here you take sort of a correlation between two spherical discrepancy for different heights of the caps. Notice that this quantity does not have to be positive anymore, because it's a correlation. Both of these guys can be positive and negative, so this could end up being negative. But so far it looks like a pretty weird identity, but there's a very nice application. So if you take G to be this function here, okay, then you can prove an identity which would relate this discrepancy, this correlation of discrepancies, to the sum of even powers of distances between points. Notice I mentioned that this doesn't have to be positive. Okay. And that's actually consistent with the fact that when the power is greater than 2, sigma is no longer a maximizer of this discrete energy. So you cannot expect that these discrete sums will be smaller than the integral with respect to the surface measure. So this was known for a long time. This goes back to a paper by Bilyk in 1956. If you consider these energy integrals with positive powers of the Euclidean distance, so it's like the Reese energy, but with positive powers. But it's positive powers, so you want to maximize. If the power is between 0 and 2, sigma surface measure is the unique maximizer among all probability measures. Okay. When the power is greater than 2, sigma is no longer a maximizer. So in this situation, everything collapses to 2 opposite points, just having all the mass concentrated at 2 opposite points. When lambda is equal to 2, then any barycentric measure, any measure with the center of mass at 0, maximizes this energy integral. Right, if you take powers that are greater than 2, sigma is no longer a maximizer, so you cannot really expect here that you would have a positive quantity between these two guys. Okay, so let's look at a different generalization. So this is due to Brauchert and Dick, so Johann Brauchert and Joseph Dick, so a few years ago. So they considered kernels of this type written here. Let me explain a couple things about these kernels, how they arise here. Again, they may look a little bit weird, but actually, first of all, notice that if beta is equal to 1, you would get precisely, this would be power 0 here, and you would get precisely the indicator of the spherical cap. And this would be precisely what we got in the computation that I showed several slides ago, because well, we precisely computed this quantity. Okay? And it turned out to be equal to 1 minus a constant times the Euclidean distance. Okay. So for other betas, this is indeed an extension. So why did they want to look at this particular extension? Well, this corresponds in a certain sense to Sobolev spaces on the sphere with higher smoothness. I don't want to go into full details, but if you just do things on an interval, imagine that you're not in the sphere, but you're on an interval, and you consider functions of the type x minus t plus. So if you consider this function, if you consider a kernel like this corresponds to integration, well, just integrating once. If you pair another function with this kernel, you would essentially that gives an integral once. If you put a power here, that corresponds to integrating several times. You can integrate by parts, and this would correspond to integrating several times. So this is a natural reproducing kernel for Sobolev spaces on the interval. Okay, now this is a very natural analog of that construction. So that's how they came up with these kernels, and indeed these kernels give you certain Sobolev spaces. I will mention on the next slide the exact smoothness that you get. You don't get exactly the smoothness given by beta, so you have to adjust it, but to get it. So for these kernels, you also get a Stolarsky principle written here. Okay, so now you have a different discrepancy. So instead of the characteristic functions here, you have these more complicated kernels. Okay, but you do get a Stolarsky principle, and let's see what they can prove. So these kernels are not as nice, but when beta is a positive integer, they have a very nice representation. So they have one part which is a polynomial of degree m minus 1, and another part which is up to a constant and a sign is the odd power of the Euclidean distance. Okay. So now that tells you that if you go back and take beta to be an integer, if you go back to this Stolarsky principle, and if you impose an additional condition that your Z is a spherical design, you would be able to replace these kernels just by the odd powers of the Euclidean distances. So you would get an identity for odd powers of Euclidean distances, but only for spherical designs. Because for spherical designs, this term will disappear, because you would have a discrete sum and the integral, and by definition for spherical designs, that's the same thing. Okay. All right, since my time is limited, I will not stop on further applications, so I just wanted to show you this sample. So another version of the Stolarsky principle. Okay, so let me move on. So I'll turn to some work by Maxim Skriganov. Again, it's only a small sample. He wrote, I think, about 6 papers related to this, but I'll give you a small sample. So he took this geometric approach to extending the Stolarsky principle. Basically, if we take an arbitrary metric space with fixed probability measure, with the property that it's distance invariant. And here distance invariant means that if we take any ball on that space, of any ball of radius r, its measure is the same independently of the center. All right. So then you can introduce a new metric, and that metric is, so this is called the symmetric difference metric. So you take 2 different balls and you take the symmetric difference between them. Okay. And then you can take an arbitrary positive weight function, okay, oops, and integrate. So here you do it for fixed radii, and then here you integrate over the radii. All right, so this will be a metric. That's easy to see that this is a metric. And this metric is actually very interesting. It has interesting properties, and it's actually exactly the metric. If you go back to the proof of the Stolarsky principle that we showed, you can write it in terms of symmetric differences instead of intersections. It will be more or less the same thing. The nice thing is this identity in the bottom. So you can write it this way. It's a L1 norm of the difference of the characteristic functions of balls. Okay, and then you further integrate with respect to R. So that tells you that the space M with either this or this metric can be isometrically embedded in L1. Okay. So that's why the version of the Stolarsky principle that I'm going to show, Maxim Skriganov called it the L1 invariance principle. And yeah, so basically almost verbatim, almost the same proof tells you that for these symmetric difference matrices, you can write the Stolarsky principle. Okay, and it works more or less the same way. Okay, now there is a slightly more specific version of this principle, which Maxim Skriganov called the L2 invariance principle, and I'll explain why it's called L2. Okay, so let's consider the connected compact 2-point homogeneous spaces. Okay, I will not give you the definition, many of you know that, but basically they're all characterized. So these are these spaces. So these are either the spheres, real Euclidean spheres, or projective spaces. All right, and then we can consider the choroidal distance, which is one of the most standard distances on these spaces. And on the sphere, it just coincides up to constants with the Euclidean distance. And if you view this distance on the projective spaces, then there is a standard representation. So basically in projective spaces, any element can be associated with a projection matrix onto that vector generated by that vector. And then you can write this as the chordal distance is equal up to a constant to the Frobenius norm, distance and the Frobenius norm between these projection matrices. Well, the Frobenius norm is essentially an L2 norm. It's the L2 norm of the matrix, which tells you that the space, any of these spaces with the chordal distance is embedded into L2. Well, for the spheres, it's obvious because it's just the Euclidean distance, and for projective spaces, it comes from this identity. So okay. Actually, the property of, so isometrically embedded. Okay. Actually, the property of being isometrically embedded into L2 is strictly stronger than being isometrically embedded into L1. However, it happens that this distance tau, can actually be represented as the symmetric difference metric, okay, with a very specific weight. 8 of r is sine of r. Okay. Actually, if you are on the sphere, then this would give you exactly the same discrepancy, because you would just change variables. Notice that here weight is given in terms of r, and we had t instead. We had the height rather than the radius of the spherical cap. If you change those variables, precisely this sign will pop up. Okay. So for the sphere, we already know this. For the projective spaces, that required proof. So that's what Maxime proved. And essentially that extension, that relation, the fact that the chordal distance can be represented as a symmetric difference metric, allowed one to prove this Stolarsky principle on the, by the way, this should be Q's, on the 2-point homogeneous spaces. And so one question that Maxime raises in that paper is, okay, so we know that the L being embedded into L2 is strictly stronger, but we know that, okay, here for one weight at least, we can have this symmetric difference, which is an L1 metric, does embed into L2. Are there any other weights which do the same thing? That's an interesting problem. Okay, so so that's why this particular version of the Stolarsky principle, Maxim Skriganov calls it the L2 principle, L2 invariance principle. Okay, so now, so I have about 9 more minutes. Okay, I'll skip well, I'll talk about one generalization here. Well, I need.
We started a little bit late, so it's more
okay,
like
so
you've got 12
like
minutes.
50, okay, about 12 minutes. Perfect. Okay. So so most of you know the notion of positive definite functions on the sphere. So the definition is that for any collection of points, if you take the matrix F applied to the Gram matrix element-wise, then this is positive semi-definite. And there are several equivalent characterizations, right? And one characterization that's particularly important for us is that being positive definite is equivalent up to a constant to sigma being the minimizer of the energy integral. Okay. So it immediately shows you that positive definite functions are also relevant to the Stolarsky principle because, well, in a lot of versions, you saw that sigma was the optimal measure, the way the Stolarsky principle is written. Okay, there is an interesting additional property of a characterization of a positive definite function is that if you take a positive definite function on the sphere, then there exists sort of a convolution square root of this function. So you can write it as this spherical convolution of little function little f with itself. And basically the idea is that if you take the Gegenbauer coefficients, then the coefficient of capital F is just the square of the coefficients of little f. Okay. It just works the same way as with Fourier series. Convolution brings you product of the coefficients. Okay. And here you can do this because by this property, these coefficients are positive. Okay. So using this representation here, together with Ryan and Feng Dai, we could obtain a fairly general version of the Stolarsky principle in the sphere. So let me just state it here. So basically it tells you that if you take the difference of for the positive definite function, we know sigma is a minimizer. So now if you take the difference between the energy of mu and the energy of sigma, it equals precisely this L2 discrepancy. This is very general, kind of abstract, but it does allow you to go back and forth between estimates for discrepancy and estimates for energy. For example, it does allow you to prove an upper bound for the optimal discrepancy in terms of the function capital F. And it also allows you to prove lower bounds in terms of the Fourier coefficients of capital F. Nice thing about this theorem, let me go back to it, is that it allows you, well, if we look at most of the versions of the Stolarsky principle that we saw before, usually the way it worked is that you could start with the notion of discrepancy and then obtain some energy. So you would take that discrepancy, you would square things out, you would integrate, and whatever came out would be your energy. Okay. It didn't allow you to go backwards. So that approach couldn't let you go backwards because well, if I gave you an arbitrary energy, we didn't know what sort of discrepancy would correspond to. So this approach allows for some reverse engineering. Okay, so you can start with an energy now, okay, and even though it's not very explicit, but through this identity that the Gegenbauer coefficients of capital F are squares of the Gegenbauer coefficients of little f, you could construct the function little f and thus construct this discrepancy. It's sort of implicit. It's also not uniquely defined because now you're taking square roots, so you could choose whatever signs you want for the coefficients of little f. But at least we know that for every energy, there is a discrepancy that corresponds. So there is actually a whole infinite family of discrepancies. Okay. Let's see. So this approach can actually be generalized to arbitrary metric spaces. So if you consider an arbitrary compact metric space, and then you consider a positive definite function of two variables in that metric space. Okay. You can define the Hilbert-Schmidt operator. Okay, so let's assume this function is continuous, so that our operator is compact. Okay, and since the function is positive definite, this operator is going to be positive. So we know that all its eigenvalues are non-negative. Okay. Okay, then there is a very nice representation of this kernel K in terms of the eigenvalues and eigenfunctions written here. So this is Mercer's theorem. So the representation itself is actually just the spectral theorem. So this is almost Immediate, well, the spectral theorem will tell you that this converges in L2, but Mercer's theorem tells you that it also converges absolutely and uniformly. Well, with this at hand, you can prove a version of the Stolarsky principle on the metric spaces. So we discussed that with Sasha Vlasuk a while ago, but we never got around to making it into a paper. But you could define the discrepancy. So there exists a function little f. If you start with this kernel k, there exists a function little f, so that when you define the notion of discrepancy this way, you have the Stolarsky identity. And actually the proof mimics the proof on the sphere, in the sense that, well, the way you define this function is you take that expansion of the kernel and you just take square roots of the coefficients, square roots of these eigenvalues, just like we took square roots of the Gegenbauer coefficients to define the little f. There is a little caveat in doing this on arbitrary metric spaces. Here, notice mu tilde is the equilibrium measure. So that's the minimizing measure. Okay, that's the analog of sigma on the unit sphere for positive definite functions. However, on the arbitrary metric space, nobody guarantees that that mu tilde will be supported on the whole space. It could be supported on some proper subset. And then this identity only holds if the support of mu is inside the support of the equilibrium measure. So you have this condition. Okay. You actually do have a lower bound here if mu is arbitrary, but you don't have the identity anymore. Okay. So well, we actually don't have nice applications for this yet, but it's curious that you can extend this principle to more or less arbitrary metric spaces. Okay, and let me see, I have about 3-4 minutes. So I will show you one curious instance, very specific. Many of the instances on the previous slides were very general, very abstract. So I will show you a curious specific instance of the Stolarsky principle, which actually helps in a certain problem from discrete geometry. So this is the so-called hemisphere Stolarsky principle. So let's assume in the definition of spherical cap discrepancy, we only take t equal to 0. Remember, t equal to 0 corresponds to a hemisphere. That corresponds to all points. So C of x 0, that's all points y such that x dot y is greater than or equal to 0. So you get a hemisphere in the direction of x. Okay? So and now let's take the discrepancy only with those caps. So instead of integrating in t, I will just take t equal to 0 and I'll just take that discrepancy. So it turns out that in this case, it's very, very easy to write down the Stolarsky principle. Okay, so you get almost the same thing as for the original Stolarsky principle, but now instead you have the geodesic distance instead of the Euclidean geodesic. You have the exact same form of the principle, but with the geodesic distance. It's actually very easy to see that if you take a look at two different hemispheres, the size of the surface measure of their intersection depends linearly on this angle between x and y, the geodesic distance between x and y. Okay. And it's actually also very easy to see that this integral here is equal to pi over 2. Okay, well, points are orthogonal on the average. Right? So you get this relation. This immediately has several consequences. Okay, by the way, so this relation here, this was proved independently by Ryan Fang Dai and myself and Maxim Skriganov in the same year, but absolutely independently, which was sort of funny. So it's a very simple observation. And Stolarsky principle has been around since 73, and somehow nobody observed it. And then in 2018, we observed this thing independently. But so there are some nice applications. So this immediately tells you that the sum, normalized sum of geodesic distances is bounded above by pi over 2, right? So you can even easily prove that for even values of n, this bound of pi over 2 is achievable, and it's achieved if and only if your set of points is symmetric. Right? It's very easy to see. Well, for the hemisphere discrepancy, that means that, roughly speaking, almost every hemisphere should contain exactly half of the points. Okay, then this L2 discrepancy will be 0. Okay, for odd discrepancy, for odd number of points, things are getting a little bit more complicated. You have a slightly more complicated structure. This can break into a symmetric set and an optimal set, optimal two-dimensional sets, a set which is a maximizer for S1. So you can have a symmetric set of points, and in addition, you could have something living on S1. So you can have quite a lot of points living on S1. Okay, and actually this this problem has a long history. So this was posed by Feyer-Stotz. He proved it in dimension 1 on the circle, and then conjectured for other dimensions. There were a series of papers where these things were proved. So I think in this full generality, we were the first ones writing it down in full generality. I don't claim that we solved the Feyer-Stotz conjecture, but this definitely gives a very simple proof. So it's a very nice application of Stolarski principle to a problem in discrete geometry. Okay, and I'm out of time, so I have quite a few more slides, but I will not go through them. I would be happy to discuss with anybody. So I'll stop here. Thank you. Thanks.
All right, thank you very much for that, the wonderful talk. Do we have any questions for the speaker?
From one of the first slides, when you were talking about the L2 spherical cap discrepancy, should the upper bound have a square root log in it? Because you said
so okay. So you do have a square root of log for the L infinity discrepancy. So for the supremum discrepancy, you have a square root of log. That's the best we know at this point. So that comes from using jittered sampling. So when you take random points in different regions, and then you use large deviation bounds, so square root of log, essentially it's the inverse of e to the negative x squared. So that's why you get the square root of log, is the inverse of the Gaussian tails, okay? Sub-Gaussian tails. For the L2 discrepancy, you don't have this, the square root of log. So if you take the L2 instead of the supremum, take the L2 average, you can prove that this lower bound is actually tight. Okay. And it's actually an open problem. We don't know what's tight for the supremum discrepancy. Okay? Whether the square root of log should be there or should not be there. It's of course just a tiny quantity compared to the order of this to the order of magnitude of the discrepancy. So that it doesn't change much, but it's still an interesting question whether the square root of log should be there or not.
So how is the upper bound achieved for the L2? Is there like a specific sequence that was?
No, you could do jittered sampling, but because you would be taking the expectation of the L2 discrepancy squared, and then you can interchange the expectation and the integral in the definition of the L2 discrepancy. Large deviation bounds do not arise in that case. And actually, the easiest way to do it would probably be using the Stolarski principle. So I mentioned here that you can compute the upper bound for jittered sampling. So that would be very easy. This would be just a one-line computation, essentially, or 2 lines. Okay. All right. Anything else?
I have a quick question. So
Hi,
there
Bernard.
is, hi, Dmitry. Hi. Great talk. Really
Thanks.
interesting. Yeah. I have a quick question. You know, there are all these integral identities, and you know, even you can change the powers of the kernels and so on. And I'm wondering if um, um, maybe there could be some underlying like pointwise equation, like a PDE in the sphere that from which you could um, derive some of this.
I
Do you
would be
think?
very interested in seeing something like that. So I don't know an answer to your question. So, but it would be very interesting. So it does make sense that there should be some PDEs underlying it because, well, you're minimizing energies, and that
Right.
often leads to PDEs. But honestly, I just don't know an answer to your question. Yeah, it would be very nice to find an approach of that type to these things. But yeah, I don't know this yet.
Sure. Okay. Yeah. Just was wondering. Thank you. Thank you.
Yep. Yeah, thanks. That's a good question.
Mhm.
So again, in the style of thinking aloud. So it seems the Stolarsky principle works nice if you have a set and then some group of isometries acting on it. So in the case of the sphere, what we are doing, a lot of these distances were averaging something. So it seemed that there should be a Stolarsky principle for Lie groups or something like that, where you average. So say the group acts on itself and you average under the action of this group or something like that.
Yeah, that should probably be possible. Yeah. Right, but the question I think always is, can you get something nice? So either you want something very general, or you want something specific and looking nice, where you get some interesting energy or interesting discrepancy or interesting metric, so something like that. Yeah, that I haven't tried. That would probably be interesting to try. Maybe we could try to do it, and maybe we could add that to this metric, arbitrary metric space, and finally finish that paper. Yeah.
Yeah, I was just so when you showed these slides where there were these complicated distances, I don't get. So is the only correct intuition about these distances is that you're averaging something under the action of this group? So around.
So which one?
Someplace closer to the beginning. When you start talking about yeah, original generalized version. So that would be
this
slide.
one. Yeah.
Yeah.
Mm-hmm.
Yes.
Right.
So what's the intuition about this? Yeah. Mm-hmm.
Right. So actually, you could. The way it was written. So I like to write it more on the sphere in terms of integration over the sphere, but you could integrate it over the over SOD. Well, SOD plus one, so you can integrate over actions. Yeah. So and that essentially gives you, in a sense, it gives you a distance of this type. So for different functions G, you get a distance of this type, and these distances arise very naturally. If you make the Stolarsky-like computations, you get these distances where you integrate. So you take the difference of distances from a given point to from two given points to all of. So you average over all of the points in your space. Yeah, it's interesting to understand what this would really mean. Yeah, and what it can give you. Yeah, so off the top of my head, I don't know, but yeah, you could consider different distances here instead of writing down, instead of putting geodesic distance here, put other distances, and you could still get some. You would get a Stolarsky principle of a similar type with some weight. Okay.
Thanks.
Other questions? I mean, so one question that I might have had was there anything from your slides that you didn't get to that you really, really also wanted to show?
Let me see. Well, okay, I'll just spend 1 minute. I won't go into any details. So this is from a joint work of Michael Lacey, myself. So you have this problem of uniform tessellations. So when you take, so if you take 2 points and on the sphere, and then you try to, then you take, say, a random hyperplane through the origin, and you ask a question: what's the probability that that random hyperplane separates those 2 points? Okay. So it's easy to see that actually that probability is equal to the normalized geodesic distance. So here, D is normalized geodesic, so the maximum distance is 1. Okay. And also, it's quite easy to see that it's equal to the surface measure of this spherical wedge here. Because basically the Z orthogonal would separate these points if Z lives in this wedge. Okay. So now if you take some collection of points, you can also look at what proportion of points separate X and Y. Well, what proportion of hyperplanes defined by those points separate X and Y. So this has relation to lots of different things, like embeddings into the Hemming cube or the so-called 1-bit compressed sensing. Okay, but from this geometrical picture, this is also a discrepancy type question. So you want these quantities, this proportion and this probability, you want them to be close, and if you want them to be close either for all X and Y, or you want them to be close on the average. But this difference is precisely a discrepancy type question. And there is a Stolarsky principle with very interesting kernel that comes up here. So if you take this discrepancy, you get this kernel, which is a attractive repulsive kernel. So it's with a minimum at 0. So it sort of tries to orthogonalize your points. It's very similar to the so-called frame potential. So the frame potential is this. Okay. So you can see that this has very similar behavior. Both of these are minimized when the points are orthogonal. Okay, so you have both of them squared. So essentially, one is the sign of the other. So the frame potential is the sign of this expression inside the parentheses. Okay. So it's interesting to understand minimizers of this discrete energy also. And there are, of course, lots of other questions about discrete energies of the sphere where we don't understand the minimizers. For example, if instead of the geodesic distances for which we understand things, you consider the acute angles, so the angles between lines generated by points. Okay, there is a conjecture about that, and it's absolutely not understood in dimensions higher than 1. And in dimension 1, you can actually prove it using a specific version of a Stolarsky principle. I probably have it somewhere here. In dimension 1, you can do Stolarsky principle for quadrant. There are many proofs of this in dimension 1, but you can also do Stolarsky proof for quadrants. Okay. Okay, so thanks for asking this. I briefly showed a couple other things that I didn't have time to show.
Sure. Any further questions? Or I guess we can switch to off record. All right.
Yeah, let's stop the recording.
Yeah. So the